Hello. All right, this is lecture 5 in applied nonlinear dynamics and nonlinear control. So I'm going to talk briefly about attracting set, dissipation in a flow, and invariant set. So remember that in varying initial conditions, we can compute the orbits of our dynamical system. In other words, we have this given system of equations, we have our initial conditions, and then we can find the state of the system as time, either in our case, in our framework, we have said that either time increases positively or the magnitude of time increases positively when time is actually negative. In other words, we have defined the flow for both positive and negative time. So now, if we draw the system's flow or trajectory in our state space, just to remind you again, state space, half of the phase space, sorry, half of the states are displacement, the other half are velocity. So this is my phase space. If I draw the flow, if I follow the flow from different initial conditions, I could have two kinds of systems. I could, if I consider this flow and say point C travels to point C prime, here the same thing, and then B to B prime, A to A prime, and D to D prime. Now if I compute this surface, this area, initially and at our final time, I could see that this area could remain constant. In other words, the area could change. It either could shrink or expand or remain constant. So if the area remains constant, then area is conserved. They say area is conserved, or the area can be contracted. And we can show that the flow is conservative or dissipative depending on whether the divergence of a vector field is 0 or negative. So vector field, as we said, is the right-hand side of our state equations. Our F's are our vector field. We can show that if the divergence of this F with respect to our state variables is 0 or negative, this area remains constant or shrinks. And then this flow is this dynamical system is said to be conservative or dissipative. So for those of us who are coming from, for example, mechanical engineering background or from applied mechanics, we know that a conservative system lacks, for example, damping in its simplest form, meaning that when we don't have damping, and if you only have conservative forces, for example, if you have only a linear spring in a mass spring system, we have a conservative system. If we add damping to that system, if you have a mass spring damper, then that's going to be a dissipative system. So if I plot the trajectory of the system in the phase space, for conservative system, this area remains constant after delta t. And for dissipative systems, when we have the damping, this area contracts or shrinks. Right? So, and this is determined, the conservation or dissipation is determined by computing the divergence of the vector field. In other words, we compute dfi to dxi sum over I. And if this was equal to 0, that system is conservative. And if this was less than 0, this system is dissipative. This can be mathematically proved. So, for example, you can look at Naifi and Balachandran's textbook, And in section 1.4 or 1.5, you can see a proof for this. And we're going to use, they use similarities between this concept and what we have in fluid mechanics to show that for conservative systems, this divergence is equal to 0, and for dissipative systems, this divergence is less than 0. The other thing I wanted to talk about was invariant set. A subset of Rn is called an invariant set if for any initial condition belonging to S, that subset of Rn, xt also belongs to S. What does it mean? It means that if I'm initially on this set, I'm gonna stay on this set for positive and negative time. Again, for our case, we follow Knifey and Balachandra's standard. We say that both positive and negative times are taken into consideration, and we call that trajectory of flow of the system, and then xt belongs to S. Now, this is an invariant set. So we have to be exactly on this invariant set. But an invariant set is also an attracting set. If you perturb the initial condition a little bit, then positive orbits initiated in this neighborhood, because we have just perturbed the system, are attracted to this set. So, for example, I could draw it this way. Say, if this was my invariant set, if I perturb my initial condition and be here, I know that after some time, I start computing the trajectory of flow of the system, and I'm going to end up on this invariant set, because this invariant set in my phases space is an attracting set. For example, like a stable limit cycle is an attracting set, because it's in an isolated solution, and if you perturb the system a little bit, we're going to end up again on that limit cycle, stable limit cycle. Now, you might be asked to compute, all right, this is my system, and as an example, show that if the system is dissipative or conservative and under what condition. So we compute the divergence of the system, df1 dx1, using this equation, plus df2 dx2 plus df3 dx3. What does it mean? For example, x2, this is at my f1. If I differentiate f1 with respect to x1, I get 0, because it only depends on x2. Then I differentiate f2 with respect to x2, I only get negative 2 times mu, and f3 with respect to x3 again. This goes to 0, right? So I end up having negative 2 times mu, right? So df1, again, with respect to x1 is 0. df3 with respect to x3 is 0. This is a constant, omega. And df2 dx2 is negative 2 times mu. So, and then you're going to say, all right, the condition for this system to be conservative is this term mu goes to 0. And if mu was larger than 0, negative 2 times mu would be less than 0. And this system would be dissipative. And you could, for those who know some applied mechanics, know that this is the equation for a forced mass spring resonator. For maps, we could have the same equation. The only difference is this time we're going to compute the determinant of this matrix. And once we computed the determinant of this matrix, we are going to investigate under what condition the norm of this determinant would be less than 1. And that condition implies the system is dissipative. You can, as a homework, you can work on Hanel map and show that under this condition, this would be dissipative. Next time, I'm going to talk about the stability. So to sum up, we talked about attracting set, we talked about dissipative and conservative flow, or dynamical systems, and then we talked about the invariant set and an attracting set. And then we're going to talk about stability. We needed this so that we can discuss the stability of a dynamical system. Thanks for paying attention.